Okay, so I want to give you now introduction to small angle scattering. So covering the range from SAXS, so small angle X-ray scattering, a short glimpse on the advantages of neutron scattering, but I think there will be also a lecture tomorrow or some tutorials. And last not least, I want to give you a little bit a glimpse on the light scattering. So before I want to start, I want to give you a short layout. So I want to we'll cover everything in two parts. So part number one is an introduction to small angle scattering, giving you introduction to the theory. So more or less something I would call personally and somehow the grad school. Then a very important aspect of the grad school is from experiments to real space, that you get to understand the real space information you get from small angle X-ray scattering. Then I want to give you some aspects of the BioSAXS, so the Hamburg school. So BioSAXS is strongly developed in Hamburg by Dimitri Zwergun, and he has developed some very sophisticated tools to analyze small angle X-ray scattering data to be applied in structural biology. Then I want to give you some, in the second part, I want to go more to SAXS applications. So covering here life science and material science using synchrotrons. So here the examples will be chemistry and hierarchical materials. Then something which is also booming in the last years is grazing incidence small angle X-ray scattering, where you get some surface sensitive information from small angle scattering. And here I want to show you some examples from biomembranes and in situ chemistry. And at the end, I want to give you a short glimpse on light scattering, and we'll cover some aspects of light scattering. So starting from the field. So small angle X-ray scattering is very prominent in soft condensed matter. So soft matter is something where you have complex fluids in the world between fluid and solid. You have here different length scales and time scales and contrasts. And what is important is you can look at equilibrium and non-equilibrium states of the structures. Examples for soft condensed matters are polymers, then surfactant systems, where you are looking at very complex phase diagrams. Here showing examples where you go from spherical micelles to tubular structures, so hexagonal phases, or here lamellar phases. And then you also can have inverted structures of the same type. So this very complex phase behavior. This will be scope of the lecture or the tutorial in the afternoon, but also in the tutorials tomorrow. Then also one very prominent topic are colloids. So looking at practical examples, this covers, for instance, the structures of DNA, block copolymers, viruses, and proteins. And what I want to also give you somehow what I mentioned before, a glimpse on the characteristic lengths and timescales. So here you see the time scales going, the length scales, sorry, going from 1 angstrom to microns. And you can cover this by molar mass. And also you can correlate the length scales to typical time scales. So covering here from range from 10 picoseconds, then you go up to microseconds, milliseconds. And at 1 micron, you are already at about 1 second time scales. And what also is important are the surfaces. Generally, small angle X-ray scattering covers everything between 1 nanometer and about 100 nanometer classically. But you can improve the resolution, then you can even reach a micron length scales in the small angle X-ray scattering field. And what is also important is that the surfaces can be measured, and I will give you later the method how you can measure this. You can measure directly in a small angle X-ray scattering experiment the inner surface of structures. And if you look here, if you have something like a few nanometer length scale or porosity of this length scale, this leads automatically to an inner surface of 1000 square meter per gram. And exactly this value can be measured easily by small angle X-ray scattering within seconds. So this is something I want to stress here. And if you now look at examples, so here you go from atoms, molecules, proteins, polymers, colloids, viruses, DNA, vesicles. So these are the topics you can usually cover by small angle X-ray scattering here. And if you combine wide angle scattering and small angle scattering in a single experiment, you can really cover everything from the atomic structure up to the supramolecular envelope here in one shot. So from the scientific topics, this means you go from microscopic atomic molecular physics and chemistry. You go to mesoscopic systems like colloid physics, chemistry, and biology. And then here you end up to the macroscopic systems and solid state physics. So going to give you some more practical examples you can cover on this nanosystems. This is the really essential pre-requirement for small X-ray scattering. You need to have nanometric structures. So looking at this, you can look at zinc sulfide nanoparticle growth. Here is an example how you can probe the growth in the liquid jet. We can really go down to microsecond time resolutions. So you see the size of the particles over time. Can look at nucleation and growth. Here, cadmium sulfide, where you can look here nicely over the evolution of the size distribution over time. Then you can move on to formation of mesoporous and crystalline materials on surfaces, or even in the aerosol phase. Here we're looking at aerosol formed nanoparticles in this form these aerosols, and automatically your self-assembly structures and droplets, which have a size of several micrometers. And if you now zoom into these droplets, you find out that the structures are having, due to the self-assembly process, nanometer-sized pores, which are highly organized. And this you can even study in form of the aerosol in small X-ray scattering. Then one very important topic are biomembranes, drug delivery systems. This is now very prominent because the COVID vaccines are mainly based on phospholipid and packaging or wrapping. So you need to somehow protect RNA in the serum until the uptake to the cell. And this is mainly done by phospholipid formulations. You can look at biomechanics. Here an example about human arteries, where you look at the network correlation of the collagen network, which is giving the strength of the human arteries. So these are very important in situ experiments where you can learn about the biomechanics from those structures and materials. And something also very prominent I mentioned in the beginning is structural biology, where can you look at the solution structure of proteins or even more complex structures. And you can resolve the low resolution envelope structure of these proteins. Okay, what I want to stress also, so this topic here will be covered in the afternoon in the tutorial, where we do some simulations and data analysis. This part here will be covered tomorrow, as well as we will try to measure some proteins also and see what we can do in the protein shape reconstruction. Okay, so going a little bit now deeper in the theory. So as I mentioned before, what you need to do is X-rays, neutron slide, you shoot on the sample, then you have some scattering very close to the beam stop at very shallow angles, and then you are recording the scattering image on the detector. And simultaneously, you can, at larger angles, you can place another detector, and then you can record the wide-angle X-ray scattering signal. So this is how a typical setup would look like. And this elderly man is André Guinier and Otto Kratky. And these are really the pioneers of small-angle X-ray scattering. So André Guinier was developing the Guinier Approximation. This is about 35. And in the 40s, late 40s, Otto Kratky was contributing to theoretical developments and also instrumental developments. Because if you look back, so for instance, X-ray diffraction was, after the discovery of X-rays, was immediately applied in the early 19th century, and it took quite a long time to get small X-ray scattering into the game. And this is mainly limited to instrumental difficulties to measure the scattered intensity at these very low angles. And because Otto Kratky and Günther Porod and many others, Otto Glatter, were working in Graz, so Austria has a very prominent role still now in small angle X-ray scattering, due to this school founded by Otto Kratky. So this is why I call it also it. You will learn about the Graz school. Okay, so coming back. So small and wide angle X-ray scattering. So small angle scattering, you measure the supramolecular envelope. And wide angle scattering, you measure the atomic molecular lattice. And why you can do this? This is a simple explanation, is related to the Bragg's law. So if you look here, this is a reformulation of the Bragg's law. And you look here at the large distances d, you're measuring small angles. So this is to measure this large distances, you measure then the small angle X-ray scattering. And if you want to look at the atomic molecular lattice, you need the small distances to probe. That means you need a wide angle scattering signal. So this is why the simple approach, what is behind. And some examples, if you look at 20 degrees for kappa K alpha radiation, 8 keV photons, you have a resolution about 0.5 nanometer. If you look at 0.09 degrees, you have to have a resolution about 10 nanometers. And if you want to measure 100 nanometers, you need to have the possibility to measure 0.09 degree in the small angle X-ray scattering signal. So this is why it was so difficult to measure this signal. So coming now to the scattered field. So here you want to measure the scattered field. So the scattering amplitudes of all coherently scattered waves from the electrons. So every electron is contributing to the scattering, and you have to have the same amplitude for each electron, but you have a different phase. So how to add these different phases to finally calculate the scattered field, this is the problem. And to do that is somehow shown up here. You have the incoming wave, here you have the scattered wave, and the problem is you have an electron placed here at the R vector. This is the center of origin. So you measure at a certain distance R, you have an electron, you have to calculate the phase difference between the scattered wave from the electron to the origin, okay? And if you do the math properly, what comes out that this phase difference is nothing else than the scattering vector, which is 2 pi divided by lambda. So this is the correlation to the wave length, and the unit vector S minus S0, which is nothing else than this phase difference here. And if its magnitude is then 4 pi divided by lambda sinus QR, and the phase difference is then phi is minus Q vector in R vector. So this is the phase difference, and then you have to sum up all the electrons with the proper phase differences. So you have to do this Q vector in R vector. And if you do it right, the sum can be replaced by an integral. The electrons will be replaced by electron density of the sample. And then the scattered electrical field is nothing else than the Fourier transformation of the electron density over the total space of the sample. So then you can split this between QR and the mean electron density. So you have a delta QR, and what comes out, so this gives a delta function, the first part, and what comes out that the scattering field is given by the Fourier transformation of the electron density difference. So this is now quite important. And now to get to intensity, you have to make this absolute square. And then you can calculate here the number of particles in the sample. And you have here the intensity from each particle. And what is now important, you have now to calculate this epsilon. So the electron electrical field absolute square, you get a double integral. And if you do it right, you can split this double integral of this double Fourier transformation in a term where you have something like a Fourier transformation, and another term which is called convolution square of the density fluctuations. So this is now something important. We will talk quite a lot about this term, giving you some glimpse now about the correlation between small angle scattering and wide angle scattering. If you take infinite lattice of atoms scaled distance by A, and if you calculate then the intensity, you get some Bragg peaks spaced with 2 pi over A. So here it's intensity versus Q. And now what is important, if you limit the dimension of the lattice, you get immediately a broadening of these reflections. What is now important is you get not only the broadening of the Bragg peaks, so 2 pi over A, but you get also the broadening of the forward direction, so in the zero direction, so around the zero scattering vector. So what you have, this is actually the small angle X-ray scattering signal, and this would be the wide angle X-ray scattering signal. What is now important is that if you have an amorphous structure, you only measure the small angle X-ray scattering signal. If you have a crystalline core, you measure also the wide angle X-ray scattering signal. So, but in both cases, you have a broadening of the reflection. Okay, so small angle X-ray scattering is nothing else than the extension of the Debye-Scherrer formula describing this broadening, and you get from the forward direction, you get the shape and the particle size. From the wide angle scattering signals, you get the lattice. From the position, you get the lattice type spacings and strain, and from the width and the shape, you get the particle size and also the lattice strain fluctuation. So this is somehow correlated to how wide angle scattering and small angle scattering somehow linked together. And now, what is now really important, this is something you nearly need to understand, is the convolution square of the density fluctuations. So what you mean here, this convolution square, what I was describing before, so it's this term here, this is the mathematical formulation, is nothing else that you take a particle here, sorry, here, this is the particle, then you take a ghost particle and you shift it at a certain distance and you calculate the overlap integral. So you can move this around, you can calculate the different overlap integrals in different directions. So what is now important, you have to take the rotational average, because usually your samples in solutions are not ordered. So you have to take the rotation average, and then you lose a lot of information. But you have then this especially average convolution square, gamma of R, which is then containing all the information you can get from a small X-ray scattering experiment. But still, even its rotation average, there's somehow like 20 to 30 parameters you can derive from this function in reciprocal, but also in real space. Okay, so if you go on, you have not only to calculate, in real space, but also in reciprocal space, you have to do the spherical average. And then you have this gamma of R square, sinus QR divided by QR. This is exactly the rotational average here. And then you have to redefine this square root convolution function by adding this R square. And then we end up by this formula where you have this somehow this Fourier transformation, sinus QR divided by QR term, multiplied by this bare distance distribution function. So now I will discuss a little bit what you can learn about the square root the convolution function. This is somehow shown up here. This is actually the scattering problem and the inverse scattering problem. So usually you have somehow particles in random orientation in solution, and you somehow this is what you want to learn from your experiment about the structure, shape, and so on, dimensions. And this is actually what you measure. You measure the scattering pattern between Qmin and Qmax. So you have a limited Q range, and you want to try to solve the inverse scattering problem. Learn from the scattering function, learn about the particle shape. And what you can do quite easily is go this direction, calculate the bare distance distribution function, and try to interpret the bare distance distribution function, which gives you quite a good insight already about the structure, the shape, dimensions of your sample. And then you can also try to calculate the square root deconvolution and calculate in certain cases also the electron density of the particles and the shape. So what is important now, if you now look at the bare distance distribution function, what is this? And what you can learn from this? So that means that you have distribution function is also something you learn from NMR about this, also something different. A parameter is exactly a length scale you measure inside your particle. You measure how this length scale is found in your particle. This gives you then this bare distribution function. What is also important is if you have non-homogeneous electron density, then the things becomes a little bit more complicated, but also I think more interesting is if you have a positive and negative electron density contrast, then you probe plus plus. Here you have a positive contribution of bare distribution function. If you be in the negative domain of the electron density, you get also here a positive contribution. If you go from one side to another, if you turn over from these regions, you have a negative contribution. So you have positive and negative contributions of a non-electron density contrast. And this is now very important for the interpretation of the bare distance distribution function. Just want to jump over this. So what you also do is somehow take the particle form factor. So you split up all the information from the electron density contrast, the shape or the volume of the particle. So volume square is the forward scattering intensity. Then you can define a particle form factor, which has the value 1 at Q equals 0. So if intensity contribution and then a shape contribution of your scattered intensity. What is now important, so for instance, for a sphere, this would give this function here, which tells you not a lot, but if you look now here at the calculation, you get this oscillatory behavior of the intensity. So you have this oscillations here, and you have also somehow a leveling of the intensity. And if you now look at the correlation between this intensity and the bare distance distribution function here, This is a comparison between spheres and oblate ellipsoid here and prolate ellipsoid. So you have here some very distinct features in reciprocal space, but you have also some very characteristic features in real space in the pair distance distribution function. And if you look here, so this have the bell shape function. This would be the sphere. What is important if you have this oblate, prolate ellipsoids, so this would give this here this extension of the pair distance distribution function, and if somehow a peak shifted to smaller values. So this is very important. Here you learn about the maximum dimension of the particle. This is also an intrinsic feature of this pair distance distribution function. If you shift the pair distance distribution function larger than the ghost particle, larger than the dimension of the particle, this levels off to 0. This is a very important feature. The pair distance distribution function, and also it starts at 0. And then it has somewhere a peak, and depending on this shape of the pair distance distribution function, you can immediately tell. So this is now an elongated particle, where you have here the cross-section term. And if you have this oblate ellipsoid, if you have this broadening of this bell shape curve for the spheres, it's you have somehow a broadener peak, and then you have to do a certain transformation to learn about the cross-sectional and or the thickness term of the pair distance distribution function. But looking now to the extreme cases, if you have now not a globular particle, but you have a rod-like particle, then you have a very distinct behavior of the intensity function. So you have here 1 over q times the cross-sectional term. I can then calculate here the cross-sectional pair distribution function, which is just the ghost particle topic in the cross-section. And then you have here again this different term for the Fourier transformation, and you have here this cross-sectional term. If you now look this for long rod-like particles, this is now very important. What you see here is you have here the Guinier regime, something you have a constant intensity, you have a 1 over q behavior, and then you have a stronger decay in the intensity here. So you have from the Guinier regime, you would learn about the length of the particle. Here you would learn about the cross-section of the particle. And the 1 over q behavior tells you that if you were one-dimensional elongated particles. Looking now at the PDDF, so yeah, that was mentioning already before. You have this elongated behavior in the cross giving by the extended structure. This can be simply explained in the ghost particle picture by shifting this prisma along this direction and calculating the overlap integral. This is then leveling off with the overlap distance here. So this is why this is going to 0. And then here you measure the dimension of the cross-section. This is somehow shown up here. If you have different dimensions, you have different cross-sectional terms, but the same length L, so it levels off the same. Here you see 0, the influence of the cross-sectional term in the pair distance distribution function. Now going to the other extreme case, these are flat particles. What it changes here, you have in 1 over q square. You have 2 dimensions, infinite dimension. You have 1 over q square dependence. You have here the intensity term, which is correlated with the thickness. So you have a 1-dimensional Fourier transformation. This means you have a cosine term, and you have the thickness distance distribution function, which is a 1-dimensional overlap integral, which is somehow shown up here. And now going to the scattering function, it has then again the features that you learn about the lateral dimension. So if you have a very thin disk, this would be the radial dimension of the disk. The 1 over q behavior is a 2-dimensional extended structure. Here you would learn about this turnover region, you learn about the thickness. Okay, and as I told you before, this is somehow you get this broad Belch, very broad behavior of the bare distance distribution function. And if you make a transformation, you will learn about the thickness dimension of the thickness. I don't want to go in detail here, but what is more important here, I would stress, is you have inhomogeneous particles. If you have inhomogeneous particles in the intensity distribution, this is very difficult to see. But if you calculate the bare distance distribution function, this is shown up here. So this is a spherical sphere. This is the bell shape. If you have two-layer electron density, if you have three-layer electron density, or if you have a four-layer electron density, you have this correspondingly this bare distance distribution oscillations, and this tells you immediately you have non-homogeneous electron density. The same thing is also valid if we calculate the P of R functions, the bare distance distribution function of elongated particles. You have again, if you have in the axial direction non-homogeneous electron densities, as shown up here. You have here, this is for a solid cylinder, and this is for a two-level electron density in the inner structure of the cylinder. So you have here this oscillation. You know immediately that you have a non-homogeneous electron density in the cross-sectional domain. So this is something very important, and more important, I think, and this is where the bare distance distribution function is really superior, is this is why you always calculate in structural biology this bare distance distribution function is if you have the formation of dimers. And here this is an example how you can assemble dimers in these four different configurations. You see there is distinct difference if you have this compact form of the dimer. This is the elongated form of the dimer. You have this extended bare distance distribution function. And here this is more or less indistinguishable. In the bare distance distribution function, there's only subtable features. But you see here, this would be the monomer. This would be the overlap integral of the dimer. So you see here, this is clearly visible in the bare distance distribution function. If you would look at the intensity, there would be almost no difference in the intensity. There are subtle difference in the intensity pattern, but very distinct difference in the bare distance distribution function. So this is something important. This is really you should keep in mind. Now looking at polydispersed systems, because what I was telling before is all the theory was giving in simplified conditions. So although the concept works fine if you have monodispersed systems, so all the structures are looking the same, and if you have diluted systems. If you switch on below polydispersity, things becomes immediately very complicated, and you even lose more information. So this is what is happening if you look at effect of polydispersity for spheres. So switching on the polydispersity, you immediately have a smearing of the intensity oscillation. And if you have, let's say, 20% polydispersity, you don't have any oscillation anymore. So here you lose all the information about the particle shape, but you still can get some information if you fix the particle's shape. Usually it's a sphere, and then you can calculate the polydispersity out of your sample for spherical particles, assuming spherical particles. What is important is you can have different intensity distributions. So if you look at the intensity distribution, so you're just having the form factor, you have here the size distribution, you integrate over all distances, and then you calculate the intensity versus Q. So looking at this, you will see that the large particles are very dominating the intensity. They were very sensitive to the large particles. If you look at the volume and the mass distribution, so here you have the volume size distribution or mass distribution or concentration distribution with concentration of particles of a certain size. And here you have to scale the form factor with the volume to calculate the proper intensity scaling. And then you calculate the intensity. So it means that if you have two populations with a difference of size, so the difference is about 1/8 in the intensity. So the large particles are scattering, the concentration is the same for the large particles as for the small particles. The large particles are scattering 8 times stronger than the smaller particles. And if you go now to the number distribution, and this is the distribution, if you look at the cross-sectional TEM image, so you're counting the number of particles of a certain size, these things are even becoming more complicated. Because in this case, the intensity of the particle scales with the 6th power of the radius. So again, doing the example of a factor of 2 in the size of two population of two particles with the same number distribution, the intensity of the large particle are 64 times higher than the small ones. So you're really dominant. The intensity is by the large particles. There's a small contribution in density for the small particles. So if people are calculating the number distribution of your sample from small angles to scattering, you have to be aware that you are mainly measuring the large particle, and the contributions on the size distribution for the small particles is really negligible. Okay, this is something important. I want to give you a take-home message. What you learn from a sample where you have no a priori information was derived by André Guinier and is now called Guinier Approximation. So if you have no information about the particles, you can just look at the very small angle, and the intensity broadening at the very small angles is related to the size of the particle. So this is somehow a Gaussian function. Can describe the intensity as a Gaussian function, where the width of the Gaussian function is given by the Guinier radius. And the Guinier radius is nothing else than like the radius of inertia of mechanics, but instead of the mass, you put here the density, you put here the electron density in the calculation. You can also define this for the pair distance distribution. It's a similar relation. You can calculate directly from the pair distance distribution function the radius of gyration. And how you derive this from the scattering pattern, you plot the logarithm of the intensity versus q square, and then you should have a linear slope, and the slope is correlated to the square of the radius of gyration. And what is also very important is here is an example from a protein solution. If you increase the concentration from 0 to 48 milligrams per milliliter, what you see here is that you decrease the radius of gyration. And this is an effect of the concentration. And you start at high concentration, you see the effect of neighboring particles. And this is somehow decreasing the effective radius of gyration. So you always have to extrapolate to 0 concentration to derive the proper radius of gyration. So if you go, for instance, to 1 milligram per milliliter, you will be already probing properly the size of the radius of gyration for infinite 0 concentration. Limit 0 concentration. Okay, so this is somehow a take-home message. Now you can also do this for the cross-section. So you remember you have this 1/cube behavior of the intensity. To measure this radius of gyration, you have to multiply the intensity versus q. Then again, you have a Gaussian behavior. And then you can calculate from the width, you can calculate the cross-sectional radius of gyration, which is correlated to the cross-sectional per distance distribution function, like in this formula, similar to the three-dimensional case. The same thing is for the thickness function. You can derive from the intensity directly the thickness of your particles. If you have this 1/q squared behavior at the low q, you have to multiply by q squared to calculate the transformation to measure the thickness radius of gyration, and then you get then directly measure the thickness of your particles, or the lamellas in this case. Okay. Now coming to something very important is the Porod limit. So the Guinier approximation is the approximation very close to the beam stop at very low Q. And I was showing you something, this change of the slope at very high Q at a different pattern. And if you do the theory correctly, what you get out that this high Q slope goes with 1/q the fourth, and you have a proportionality factor which is related to the electron density contrast, and then another factor is the inner surface of your sample. So by measuring the Porod slope at high Q, so that means you plot a logarithm of the intensity versus logarithm of Q, you get a linear behavior. And this slope is directly related, which has the power of 4. It's directly related, the proportionality constant here is directly related to the inner surface of your sample. There are also deviations from this behavior. So you have this power of 4 behavior. And this important, so which I was mentioning before, for elongated structures, you have 1/q behavior. For lamellar structures, you have 1/q squared behavior. And if you have a behavior between the power law between 1 and 3, you're measuring mass fractals. And so you measure, the mass is not proportional to the power of the third, but is changing with a different power law behavior. And this power law behavior can be measured directly from the Porod slope with small angle X-ray scattering. And then you can also have surface fractals, so that the surface is having a rough appearance, and the surface area is scaling between 2 and 3. And also this is reflected in the power law. So 6 minus ds, if ds is going between 2 and 3, the power law goes between 3 and 4. So if you measure a power law about 3 and 4, then you can measure surface fractals. So what is also important is, as this is so easy to measure, and for instance, if chemical reactions, and they are always like in aerosols or aeroformed particles or nucleation and growth, and you have surface limited reactions and so on. By the power law, you can measure the type of reactions, because there are lists in the literature where people were making simulation and simulating different reactions. So you get a different power law. You can directly correlate the power law to the type of reaction you have really happening in your sample. So now a short glimpse, because I was talking mainly about X-rays now. So what is going on if you would use neutrons? So X-rays, you have the electron density as contrast. For neutrons, as you have a nuclear interactions, which I think you have also heard before, you have the electron, the neutron electron, the scattering length contrast. So this is scattering length density contrast. Why neutrons are very important for small angle X-ray scattering is shown up here. So if you have simple water and the heavy water, so that deuterated water. So what is changing here? You have the change in the contrast from a negative contrast to a very high positive contrast. So it goes from minus 0.3 to about 6.5. The electron density, the neutron scattering length contrast. Now looking at different structures, so if you're looking at proteins, lipid head groups or hydrocarbon chains, and RNA or protein, deuterated proteins, where you exchange selectively the hydrogen by deuterium in the protein, so you get a very deep electron neutron scattering length contrast. And by changing the water to heavy water ratio, you can match easily the different electron scattering length contrasts for neutrons. So by, for instance, you can selectively switch off parts of your sample and can recover what is the remaining part is scattering. And by doing this for various points, you then calculate for instance, the complex shape of proteins by doing this job for different selectively deuterated parts of the proteins or the RNA. Somehow shown up here, a sketch where you have a room where Lola is somehow contrast match, is invisible, and here a monster is knocking at the door, and Harold is opening the door. Harold has a very high contrast, is easily seen by the monster and the wood, and so Harold is somehow catched by the neutrons, whereas Lola is invisible. Okay, you can do this the same thing with X-rays also. There is this anomalous contrast where you change the energy of the incoming photons, and very close to the absorption edge, you have a very strong dependence of the real part of the scattering length for the electrons, and this somehow can be used to change the contrast. This is now very important if you have, for instance, counter ions in solution. You can tune the contrast to resolve selectively the counter ions if you have core shell particles. And then you want to learn about the shell, the constitution of the shell. You can tune to selectively to one part, the shell or the core, the electron density contrast, and by comparing different electron density contrasts by measurements of different energies, you can selectively find out where is sitting what, either one component in the shell or one component more in the core. Okay, so now coming up to the scattering problem and the inverse scattering problem. So how I was showing you before theoretically, but how you really solve it in reality to go from the scattering pattern to the bare distance distribution function I want to show you here. So usually what you do is, what is easy is if you have a particle, you have a certain bare distance distribution function here. You have a Fourier transformation, you can calculate the scattering. Doing now the experiment, you have different effects of the geometry and also of the radiation. You have some convolution integrals, so from the collimation, and then the convolution integral of the wavelengths distribution, and then you get the experimental pattern. So you see here immediately you are still smoothing to this geometrical and wavelengths effect. The pattern, you add statistical errors, and then you're up with an experimental data curve. So in this direction, it's easy, but how you go back from reciprocal space to real space, this is somehow shown up. And exactly you follow the same direction. You're taking here functions which are representing the pair distance distribution functions. These are p-cubic splines here in this case, but there could be also other functions. So you have a sum of these p-cubic splines, and this development coefficients of the p-cubic splines would represent the pair distribution function. So you take these functions, you make the Fourier transformation, you make the convolution, the collimation effects and the wavelength effects, you add to this to get then a function system here, which is then fitted to the experimental data. And the development functions of this fitting function here are describing the development coefficients for the pair distribution function. So fitting this data on the experimental data are also determining the pair distribution function in real space. So this is easy. You can do this, and there are several programs you can do this. It could be this indirect Fourier transformation from Otto Glatter, or the GNOME program from Dimitri Zvergun, working in a very similar way. And then you can calculate really from the experimental data the pair distance distribution function. And what is the beauty is you take the same concept, you take, for instance, arbitrary shape, you have the three-dimensional pair distance distribution function, you have a different transformation, then you can calculate the cylindrical symmetry, or you have a different transformation and here calculate the lamellar symmetry. So the equations, the method is the same, but just the kernels or the integrals is what differs. But you have the same concept. You can take different, solve different problems. Also, the size distribution can be solved in the same problem in one shot. Okay, so we managed now to go from the measured scattering pattern to calculate the pair distance distribution function. And now the question is how you go this way down here to calculate the electron density as a function of the radius. So really solve the scattering problem. And this can be done at specific symmetry conditions. Could be either spherical symmetry or really axial symmetry in cylindrical systems, or just thickness relation for plate-like systems. And what how you solve this problem here, and assuming this symmetry relations, this is somehow shown up in the next steps. So you have again a similar concept. You expand the electron density as a function of spline function, space at a certain distances. And again, you have development coefficients. So that means you have here, this is the electron density map you want to calculate. So you have here this rings where with contrast electron density. So then you have the different contributions of the rings, and then you have to calculate the convolution square. And then you end up, if you do the math right, you get the convolution integral. So this would be the self-convolution. You take the ring with itself. If here this development coefficient, but you have also the cross terms. And this you can sit down really and do the math by yourself. Here you take the spherical shell here, a large one and a small one. You can calculate really the overlap integrals of the interpenetrating spherical shell and calculate exactly these terms here. And then you can have the cross terms for the development constant. So we have set up somehow the mass. So you have somehow the influence of development functions. So the development coefficient and the pair distance distribution function. But how you can solve this is somehow shown up here. You calculate somehow a difference function. You start from a pair distribution function here. You calculate the difference pattern in the pair distribution function. This, if you calculate the mass in the development coefficients, you have a starting configuration is the different configuration. These are the cross terms. And you go on with the mass. You end up omitting second order terms and cross terms. You're omitting with a linear equation, where here this is the difference term, and this is the difference for the new iteration, and this is the term for the overlap integrals, where you have to take into account in this linear equation. So this is now, you end up with a linear equation where here you have the matrix elements, and then you can start iteratively and try to improve the coefficients. This is always an ill-proposed problem, so you have to introduce something like a stabilizer of the solution. You tell that the final solution is not highly oscillating. You have something, a linear correlation between neighboring coefficients. This somehow can be done properly, and this is can be solved in the program of DECON developed by Otto Glatter. So you can really solve this problem and calculate the electron density map without a priori information about the sample. You just assume specific symmetries. And also, if the symmetry is not really valid, it's still okay and doable. Going now to the still more complex system is if you go away from the assumption of diluted samples, you have somehow concentrated samples. And what you start to see is the interference of neighboring particles. So you get a structure factor of the particles, which is then modifying the form factor. So if you have diluted particles, the structure factor is 1. If you have concentrated, you have particles, you have an influence of the structure factor. So you have the form factor now, which is correlated with the pair distance distribution function, with the structure factor, which is correlated in the correlation function of the particles to themselves in solution. So this is now quite a hard problem you try to solve. And what is important here is that exactly this pair distance distribution function and the total correlation function, GR minus 1 square, are having the same behavior, and they are also acting the same regime to each other. So if you have a certain neighboring distance R of the particle, this is strictly related to the dimension of the particles. Okay, and this means you cannot decouple them without any a priori knowledge. But what you can do is you can introduce a structure factor, you can introduce a certain pair correlation function, and then you can fit the structure factor simultaneously to this pair distance distribution function model. And then you can calculate the pair distance distribution function even in concentrated systems. And this is then solved in the program GIFT, which is also quite funny. GIFT means poison in German. So it's a very difficult problem, but doable. Then this leads to this general indirect Fourier transformation method. Okay, just go you on and go now a little bit to structural biology and looking at the ATSAS package, which introduces a general principle of SAXS modeling. And what is now, I think, quite impressive is that from one-dimensional scattering data, where you have the total rotational leverage of your data, that means you take your your particle rotate in all directions, you lose a lot of this information here about this directional information here from the particles. You calculate the bare distance distribution function in a certain sense, and still, if you make this rotation average, you are able to compute three-dimensional models out of one-dimensional scattering data. So what you need to do is somehow a nonlinear research. You minimize somehow the difference between a model and the experimental data, but you have to add some constraints, because there are almost infinite solutions to this problem, and you're only looking to a certain type of solution, and this makes possible why you can solve this problem. And what is now important are these constraints and restraints you have to introduce to solve the problem and calculate the models from modeling through scattering data. So you can use, for instance, electron microscopy to somehow limit the search volume. And this is important if you make an ab initio shape reconstructions. You take the data from crystallography and NMR, you have a high resolution atomic models. You add these atomic models as fixed parts in the solution, and then you somehow modify just different rigid bodies, and then you get extremely high resolution, extremely high quality data from the three-dimensional models if you fix atomic models. Can also add missing fragments. You have some parts known, some parts are missing, so you can add just missing fragments to the known part. You know where certain parts of proteins are somehow interacting. This is also limiting resolution. This is also very important for rigid body modeling, when you know where another body has to attach. And also you can work on flexible systems. So all this information you need to couple in, and then you are able to solve the problem, the inverse problem for this solution structures. But you always have to keep in mind it's a low resolution method, and you have to be suspicious about the solution and check what you get is really true and compatible with the information you get from other methods. Okay, so in simple words, again, this you minimizing the chi-square, the difference between the experimental data and the model. You have to add some constraints, and this is what you actually then try to measure. So you have some penalty functions which are adding this additional information, and then you're not modeling just simply chi-square, but you're modeling on the whole functional system with this penalty functions. So a simple and very impressive case is the ab initio shape determination. This is something we will try to run also tomorrow at the experiments and see how far we can go. The trick is there, from the bare distance distribution function, you can calculate from the scattering data a maximum dimension of the particle. In the first instance, you fill everything. The whole volume is the particle. And when you try to fit then the data, you get a very strong difference comparing to the experimental data. And then you start converting beads into solvent. You're moving beads, in other words, and then slowly you will converge and you will fit properly the experimental data. But what will happen is that you will have perfect fit for these three different models. But what you know and what you actually do with this penalty function is that you're looking for a compact solution. So you will squeeze or a white solution, we have this fuzzy interface here, and also detached beads. So this solution will be omitted, and you somehow converge to this smooth three-dimensional shape of your particle. And now what you do is actually you're not running it once, you're running it 40 times. And what you see is there will be some parts of the shape conserved in all models, and then you will have something like this fuzzy interface. And this is actually somehow reflecting the resolution of the model. So you know, in the part which is seen in all models, this is somehow the part you know, which will be correct, and this fuzzy interface is the resolution limit of the method. And usually is the resolution limit is in the order of 1 nanometer, and this is actually quite high. But what is important is if you have constructs, even this low resolution structures gives you already some insights. And this is somehow shown up here. This is an example. Now I will move on. Well, time is running. Move on to the CDC45 protein, which is conserved in our eukaryotes, and it's important in the initiation of the DNA replication to the cell dividing cycle. And what we did is we grabbed this purified protein at a concentration of about 2 milligrams per milliliter. We needed to have about 40 microliters. And we put it in the beam, made a 30-second exposure, and get this scattering pattern. But even if the quality of this pattern is not very high, this part here, this initial part here, contains the information of the shape. And what we did here is really to do this 3D-dimensional modeling, Amenitsch modeling, and then we're adding some known parts from similar proteins from other species. And so we have the blue part we can add and identify in the model, the three-dimensional reconstruct, and also the yellow part from another protein crystallography structure. What also quite interesting is there is this missing fragments making this part here, and just by enzymatically cleaving off this part, the people were able to crystallize the remaining part easily. Now, before it was not possible due to this flexible part here coming out from this three-dimensional model. So this is somehow show you how important can be the SAXS solution structure. Can also make multi-phase speed modeling, making many measurements with neutrons at different contrasts, different single fragments, and then you add all this information. You can also add information from the complex. Just by dummy shape bead modeling, you get roughly the overall shape of the complex. But adding all this information from the single beads, from the single structures, you can really reconstruct really the assembly of the whole construct in quite nice and way. But you need to do a lot of experiments and really check if the outcome is really compatible with the knowledge you have from the structures. Something also very easy is shown up here. So if you have a crystallographic data available from your protein, what is a very easy experiment is just to take the protein, add it in solution, purified, and then you can use the data from the PDB to calculate the scattering just from the X-ray, from the structure data. But then you have to incorporate it. You have in protein structures excluded volumes. And also very important, you have hydration shell around the protein, which is adding to the scattering. And this is actually a quite important contribution, this shell. And so in other words, you have here the atomic scattering in vacuum. Then you have the scattering from the excluded volume. So that means you add up with this shape here. And then you have to add the scattering from the hydration shell. There are some programs like Chrysol and Trison from Svergon, but there is also Foxit. There are new versions of Chrysol available at the ATSAS package. And this is quite an easy experiment and quite an important experiment. And how important is the shell? This is shown up here. This is from lysozyme. This is the scattering from lysozyme in vacuum. And the blue curve is the scattering from lysozyme, taking the shape effect and the border effect. So the hydration shell effect into account, you have a drastic change of the scattering intensity. So this would be the border alone. So you see that's quite a substantial contribution to the scattering. So this is somehow ending of the first part. So I have now still 15 minutes to run the second part, and I only want to give you maybe two snapshots. In the second part, so why small angle X-ray scattering is very interesting is you can control the sample conditions very efficiently and very precise. You can easily change the temperature, you can pressure, you can put mechanical force, you can do a single particle experiment, you can change the chemical potential. So you can, and what is also important, you can do not only static experiment, but also in situ experiments. You can really see how your sample is looking at any moment of the reaction. And I want to just show you here one example from Nature Chemistry. This is a quite old example. So here we're looking at polyoxymetallate clusters. So this molecules here. So there are some metalloxymetallate clusters, which are coordinated by these rubidium atoms. So this has a dimension of about 2 nanometer, here a dimension of about 1 nanometer. And if you put them on functionalized carbon nanotubes, where you have some dendrimers, which are charged, also this rubidium metalloxymetallate clusters are somehow charged, so they interact immediately and form something like a layer. And this structure here has extremely high efficiency for water splitting. What people know from XEDS elemental mapping is, here you see the carbon, you have something like a carbon core. Here you see the tungsten. So you have something like a shell around. The high resolution TEM, you see here the multi-wall carbon nanotubes in this layered structure. You have a 2 nanometer shell around, but you don't know anything about the coordination or the insights about the shell. So now you can do a small X-ray scattering experiment. You just look at the functionalized carbon nanotubes. So you get the red curve. You can look at the polyoxymetallate clusters in solution. You get the blue curve. And if you put both things together, you can get really this very nice peak. And what you learn about this peak is that there's somehow highly ordered layer of the polyoxymetallate clusters on the surface, which is not easy, not at all visible in the high resolution TEM. So this is something very important. Can also look at now a little bit on the solution structure. So you can use, for instance, the crystallographic data from the roof for POM. You You can also look at the crystallographic data from the precursor. You can calculate with chrysal the scattering pattern. Then you can take this scattering pattern and calculate a model, which is this ellipsoidal model here, and double ellipsoid model here. And you can now fit these models onto the data, and you can learn also not only about the shape of the root bomb in solution, you can also learn about the structure factor, which is this shoulder here. This is the structure factor. This part here would be the form factor at high Q. But I want to show you something important is, and there are many, fortunately, you don't need to nowadays to really develop models, because models are programmed in many software packages. And what they will do is you just assume a shape of your particles, and then you somehow do this spherical average inside the software. And then you can make also here some stacking. So this is actually, you take here, this is the form factor square, and this is this rotational average, and this gives you then the scattered intensity. And this is somehow can be easily done. Here it's explicitly shown for this model. You need not to worry about. There are many software packages available where you can really do this operation. So something I want to jump over now, giving you, if I can stop my presentation, I would be happy. Yes. I want to go to the last part. Show you here a glimpse on grazing incidence modeling X-ray scattering. So we want to look now on liposomes, which is also very important in the afternoon lecture. So you're looking at ordered structures where you have something like a self-assembly of these phospholipid bilayers. You're making a one-dimensional crystal. Okay, so phospholipids are very important for cell membranes. So this is why they're important for biology. And we want to look at exactly these structures, either in solution or deposited on surfaces. So in one case, if you look at the solution, you would get these ring-like structures. Okay, so you would like this, measure this in scattered patterns. If you look now in surfaces, and you have this elongated planar structures, so they self-assembly and reorder themselves on the surface. And you're not getting this diffraction rings anymore, like in powder diffraction, but you get diffraction peaks to the one-dimensional alignment in out-of-plane direction, and also in plane direction if you have in-plane order, and this would be the out-of-plane order. So this is now important. You have an extremely nice information gain doing this experiment in grazing incidence modeling X-ray scattering. You become extremely sensitive to the surface layer, and you have some problems now. Is that you're measuring here the intensity is the Fourier transformation, the two-dimensional Fourier transformation of the electron density contrast. But then you have the fact that you have a certain geometry. You cannot go with the incident beam through the sample. Usually you cannot have the scattered beam going through the sample. The maximum is either going parallel to the surface for the incoming or exit scattered beam. This is something important. And also that you have transmission coefficients going with the beam going through into the sample and out to the sample. So you have some refractional coefficients. So the simple theory has to be modified by this transmission coefficients here for the incoming for the scattered beam. So what you have due to the refraction effect enhancement of the intensity, this gives you the rise to this Unada wings. This is exactly this effect of this transmission coefficients here. And then, depending on what kind of experiment you're doing an omega 2 theta scan, so measuring along this vertical plane here in reciprocal space. So change the incident angle, you change the exit angle, and you just measure at this theta to theta conditions. So you're probing these points along this QZ direction. So this would be a reflectivity scan. You can also work on a fully open detector. So you would the reciprocal space by the intersection with the Ewald sphere. This is also something very a usual measurement. What you do, you fix the incident angle, and then you have a fully open detector. So you're measuring all the intensity on the Ewald sphere, or you fix a certain scattering amplitude of the scattering vector, and then you rotate simultaneously. So you fix the Q vector, and then you rotate it in this direction through the sample, and then you make an omega scan. And depending on which type of scan, you learn different features. For instance, the omega scan is very important if you want to know about the degree of ordering of your sample on the surface. But this is the easy approach, but the things are even still more complicated. And actually, what is happening is exactly when you are very close to the total reflection on the surface. So this is what the thing what we have discussed before. You have the incoming beam, you have refraction effect, transmission effects. You have here the scattering event. Here you measure the scattering intensity. But if you go very close to the total reflection angle, sorry, we have to add different effects to the total reflection from the substrate. And you can have the total reflection from the incoming beam. You have to have the total reflection from the scattered beam, and you could have the total reflection from the incoming beam and the scattered beam. So this is quite interesting. So this would give the same scattered angle for these processes. Here you have a shift of the scattered angle. So you have two contributions here, this two and this two, which could give the scattered angle. And this is called then the distorted wave point approximation. And this is actually what you need to solve to evaluate properly the data in the grazing incident geometry. Okay, just want to jump over this part. I want to just show you exactly this thing here. So I want to look at in situ chemistry on surfaces, looking at soil shell chemistry, where I have a surfactant mesophase, and looking at the self-assembly process. So you're making a meso-structured hybrid structures, and you end up with mesoporous materials with very high organized porosity. So you have this extremely highly ordered porosity in the material, and you can work with this process is called evaporation-induced self-assembly, and you can make thin films, you can make monoliths, or you can make particles in aerosols. And what is interesting, you just need to change the surfactants. So you can change directly, which is so that the surfactants is determining the pore size. You can tune the pore size by changing the surfactants and by changing the anorganic precursors in the soil shell chemistry. You can modify the wall constitution. And what I think is a quite nice example is when you simply mix everything together and start a reaction. So this is, you have this somehow the solution here. So at time equals 0, sorry. At time equals 0, you start a reaction. You remove the cursor, the solution. You have a film formation. You can look at the film thickness by lights interference pattern, and with synchrotron radiation and the mesostructure formation. And if we now look here at at the results, I think this is quite impressive. So here you're looking at this chemistry, aging time and relative humidity was the variable they introduced, or we introduced. And then here you're looking at the pattern and the film formation simultaneously in situ. And if you start now the movie, you see that all of a sudden you go to a lamellar phase, you have this pattern here. And shortly after, you have these spots here, you have a hexagonal phase. And if you move on, you get a more complex pattern, which is a cubic phase. This is the PM3N phase. And at the end, you end up with this long stage, you end up with another cubic phase, which looks actually like a hexagonal phase here. So what is now important, what you learn here, is that you have an initial solution where you have surfactant, water, ethanol, the inorganic precursors, HCl. Ethanol is evaporating during the film formation. You have a very thick film in the beginning. If the ethanol formation, the film thickness is shrinking over time. So you have isotropic solution, everything is possible. And if you move on, you have the film formation. There's something like a self-assembly process going on. And at the end, you have this extended condensation structure. So you have this surfactant structure, which is forming the pores. And here you have the condensation of the organic species around. And what is important here is that you have this intermediate regime where you have water and ethanol available. And what is important is that you have, from the chemistry, you have the quantity of surfactant and the quantity of the inorganic precursors is fixed due to the chemistry. And you have to be somehow stabilize this. And the only free quantity is water. So just by controlling the water, by letting evaporate water or absorb water by controlling the external humidity, you can change exactly the mesophase, the final mesophase you form during the reaction. And this is something I think quite important. You learn exactly from this in situ experiments. Okay, so I want to jump over this one. I want to conclude. Well, actually, I wanted to show you something about light scattering. Just want to show you these two slides here. So this is important here. This is the comparison between light scattering and X-ray and neutron scattering. So you have here the dimensions. You go up from 10 to 100 nanometer. You have the Rayleigh-Ganz regime, also very matching very well with the smaller X-ray scattering regime. Then in this regime here, which is easily accessible with light scattering, you change the theory and it becomes very complicated. So this is called Lorentz mean regime, but you still can do data interpretation, taking into account this Lorentz mean regime. And last not least, you end up here with the Fraunhofer diffraction. So the important thing is that the phase shift is determining which kind of theory is taking place. And what is important that the concepts with the pair distance distribution function can calculate from the light scattering data are still somehow conserved even in the Lorentz mean regime. And here we learn about the shape of the scatterers and the size of the scatterers, just looking at the bare distance distribution function, even if you have to take into account the Lorentz-Mean scattering. So even if the Rayleigh-de-Begans is strong, methods valid for the Rayleigh-de-Begans can be applied, and to learn about these things. This is something I want to stress, and something else that this is shown up here from the dynamic light scattering. And dynamic light scattering, you not measuring the intensity as a function of the scattering angle. You're fixing the angle and looking at the intensity fluctuations, and looking at the learning from the intensity fluctuations is something like the correlation function of the intensity fluctuations gives you information about the diffusion constant. And this is really important in light scattering. Actually, you only measure the diffusion constant. This is somehow up, so you define here the correlation function. You have here you define here the formalism for measuring the diffusion constant. So it's this is the diffusion constant as a function of the Q square multiplied by Q square and a correlation time, tau, of the correlation function. So this is what you measure, actually, the diffusion constant. And what you do at experimental, you correlate the diffusion constant with the hydrodynamic radius RH by this Stokes-Einstein equation. And what you also can learn is, even if you have concentrated systems, you still measure the diffusion constant, but you have some effects with the concentration. So this gives you quite nice insight if you measure different soil concentrations about the change of dynamics, tells you about the interaction of the particles. So this is quite interesting. So coming to the conclusion. So introduction tells you about the Graz school. I was going from experiments to real space, telling you a little bit of BioSAXS, the Hamburg school, showing you some examples and give you a glimpse on grazing, incidence modeling, X-ray scattering, which is quite powerful at the end, and very used technique recently in science. Can look up our annual reports where you learn quite a lot about different systems and what can you do with small angle X-ray scattering. And I want to conclude here with this picture, SAXS on the beach. And actually, this is also something related to you. These are pictures we do with a SAXS course in summer. And these are the opportunities you would have if you would do the HERCULES school in presence. You could enjoy some beach life here with stand-up paddling or swimming on the beach, or some night events we also do with the students. There's some very typical restaurants here in Dresden, which are called the Smitzer, which are a very peculiar and very interesting part of Trieste. So maybe next time, if we have the chance, and we can do this school school in presence, you can take benefit and profit of this social events. And what I'm very sorry that this very important thing is missing at HERCULES. Okay, thank you for your attention.